In this video, I am going to discuss the design of such snubber circuit for SCR. What is meant by snubber circuit? What is the purpose of snubber circuit? Snubber circuit is defined as the circuit in which the series combination of a capacitor and a resistor connected across or in parallel to the SCR to prevent the dV by dt triggering across SCR and to limit di by dt through SCR and to minimize the power loss during switching operation of SCR, right? So for these three purposes, a circuit is used which is known as snubber circuit. Now let us see step by step, right? First of all, dV by dt triggering. In order to understand these three, I would like to draw a simple circuit in which we have SCR, load and a source. Okay, so this is a simple circuit in which a load is controlled by a controlled switch called as an SCR. This is the source, considered to be a sinusoidal input voltage. Okay, so Vm sin omega t, and there is an SCR, and this is the load. Okay, so here the current flowing through the load and voltage applied across the load is controlled by this switch called as SCR. Okay, so now let us see. Here there are two ratings of SCR. There are several ratings, among them mainly in this regard we need to consider two ratings of SCR, that is dV by dt rating and di by dt rating. Okay, so you know always SCR must be operated within the specified ratings or limits given to SCR. Okay, so there is specified dV by dt rating and specified di by dt rating. So the voltage, otherwise the rate of change of voltage across SCR always must be less than that of the specified dV by dt rating of SCR. Similarly, the rate of change of current flowing through the SCR at any instant or in any circumstances must be always less than that of the specified di by dt rating of the SCR. Okay, so suppose if there is high rate of change of voltage across SCR, then you know SCR will be triggered without giving gate pulse to SCR. So this type of triggering is known as unwanted triggering or false triggering. So here SCR must be prevented from such type of false triggering or unwanted triggering, right? And not only that, high rate of change of current flowing through the SCR, okay, causes the hot spots in the device or causes hot spots in the SCR due to high current density in the region of gate connection. So that is why here these two ratings must be less than that of the specified ratings given to the SCR. Okay, so now let us see how dV by dt triggering can be prevented. Okay, so which is appeared across SCR. So there are some certain passive elements, right? So we can call them as a resistor, capacitor and inductor. So we know that the resistance is a property of a substance which opposes the flow of electron through it. So similarly, inductor is there. Inductor is so it is an element which opposes the rate of change of current flowing through it, right? Similarly, as a capacitor is okay an element which opposes the rate of change of voltage across it. So here, in order to prevent dV by dt triggering, okay, the capacitor can easily prevent this type of triggering. Why? Capacitor is an element which is opposing the rate of change of voltage across it. So that is why, so the rate of change of voltage, that means dV by dt, prevented by using a capacitor connected in parallel with SCR. Okay, so that is why here we can connect a capacitor in parallel with SCR in order to prevent the dV by dt triggering of or for unwanted triggering or false triggering of an SCR. So this is a capacitor, right? So now let us see here how this capacitor is preventing dV by dt across SCR. Let us assume initially SCR is in off state. That means SCR is in forward blocking state. Okay, so during forward blocking state of an SCR, for sudden voltage applied across the capacitor, it behaves like short circuit. So when capacitor is behaving like short circuit here, we can easily understand that the short circuit voltage is 0 and the short circuit current is infinitive. That means, here since it is got short circuited, the voltage across capacitor is at initial stage is 0. Okay, so that means so at the time of starting, that means initially capacitor voltage is 0. That means the voltage appeared across the capacitor is 0, means the same voltage is also appeared across the SCR, because SCR and capacitor are connected in parallel to each other. So that is why voltage is common for to these two branches. Okay, so that means here by connecting this capacitor in parallel with the SCR, we can conclude one point that here at initial stage, that means the sudden change of voltage across SCR made 0, right? So in the presence of this capacitor it happens. If there is no capacitor, the sudden change of voltage across SCR cannot be 0. Okay, right? And secondly, so whenever it is in off state, capacitor is short circuited, it tries to charge. Okay, it tries to charge. Okay, so in this direction, okay, through the load, right, and through this path. So in this direction, that means in this path, capacitor gets charged. So capacitor gets charged to the input voltage Vm sin omega t. Okay, so now capacitor is completely got charged, right? Let us now apply firing pulse to the SCR so that it may be turned on. That means I am turning on the SCR, giving firing pulse. So when SCR is turned on, immediately the current flowing to the capacitor gets reversed because it gets discharged. Capacitor, as soon as capacitor completely charged to certain voltage, it immediately discharges. Okay, so as soon as I turned on this SCR, capacitor starts to discharge. So the discharging current flowing through the capacitor is in reverse direction. Okay, so in this reverse direction, capacitor discharging current is there, but it flows through SCR, right, and through capacitor. Why? Because here discharging current doesn't take path like this, because here SCR is turned on. Let us say simply, SCR is working as a switch here. When switch is closed, SCR has short circuited. SCR is short circuited, that means it is turned on. So that is why the current flowing through the SCR is very high. So because of this high rate of change of discharging current flowing through the SCR, there will be occurrence of hot spots in the device because high current density in the region of gate connection. So then it may cause SCR to get damaged. So that is why in order to limit such high rate of change of current flowing through the SCR, right, we need to incorporate another element in this particular circuit. So that element may be resistor, because resistor is an element which limits the current flowing through it. So that is why here I can draw another circuit in which we can see a resistance. So this is the actual snubber circuit for an SCR, right? So now here I have incorporated a resistance in series with the capacitance. Now you see, during discharging period of capacitance, okay, the high rate of change of current flowing through the SCR whenever it is in on state is limited by this resistance. Okay, so connecting this resistance, okay, we are limiting the high rate of change of current flowing through the SCR. So this is what the design of snubber circuit. Here we can see two elements, that is a capacitor and a resistor connected in series, this combination is connected in parallel with thyristor. Okay, so it is used to prevent dV by dt triggering, to limit di by dt through SCR. Now let us see how to understand the minimization of power loss of this switch, right? When switch is getting turned on and getting turned off, or switching, during switching operation there are certain power losses. Now in order to understand, okay, I would like to draw a waveform, okay, waveforms in which we can see how the power losses are minimized, right? So here there is a voltage across the thyristor and there is the current flowing through the thyristor. Okay, okay, suppose let us assume that initially there is current flowing through the SCR. SCR current, there is current flowing through the SCR whenever it is in on state. So that is why there is certain amount of magnitude of current flowing through it. So that is what we can say. So as long as SCR is in on state, there is current significantly flowing through it. So that is why we can show it during on state of the SCR. So let us consider this is on state. This is on state of SCR. Right? So at the same time, the voltage across the SCR is 0. Right? At the same time, the voltage across SCR is 0 because SCR is working like short circuit or closed circuit whenever it is in on state. So for short circuit, the voltage across SCR is very minimum. Practically it is 1.5 to 2 volt, but ideally we take it as 0. Okay, ideally we take it as 0. Here 0 we have considered. So this is during turn on period of SCR. So when SCR is turned off, what happened here? When SCR is turned off, okay, so the current flowing through the SCR is 0. So that is why here 0 current is flowing through SCR. So this is with respect to time. Okay, so current flowing through the SCR is 0. So that means during this particular period, okay, SCR is in off state. So SCR is in off state. Okay, so now let us observe that when SCR is in off state, there is a voltage, some certain voltage appeared across the SCR. So that is why ideally we can take that voltage as like this. Okay, let us assume the voltage is like this. Okay, so the voltage across SCR is appeared to be like this. Or if it is sinusoidal waveform, you know, so we need to take sinusoidal. Okay, so but in order to understand, I am taking simply like this. Okay, so here during turn off period of SCR, okay, there is certain voltage across, right, SCR. Now here let us consider the power loss. Power is measured as the product of voltage and current, right? So now let us consider here during this period, you know, so during turn on period of SCR there is certain magnitude of okay, here we can see there is certain magnitude of current and 0 voltage. So that means here there is 0 power appeared. So suppose if this load is not purely resistive load, so during turn off period of SCR there is a linear decrease in current flowing through the SCR, there is linear increase in current voltage across the SCR. So when we multiply these two, we may have approximately the power loss across the SCR is this much. During turn on period of SCR, there is current flowing through the SCR. Whenever SCR is in turn off position or in forward blocking state, the current flowing through the SCR is linearly decreased. Okay, so then whenever again it is turned on, there is current increase flowing through the SCR. At the same time, if you consider the voltage waveform, that is voltage across thyristor Vt, okay, so the voltage across thyristor during turn on position of SCR is 0, and whenever it is in off state, then the voltage appeared across thyristor may be increased. So let us assume these are a linear decrease in current flowing through the SCR during turn off period of SCR, and there is linear increase in voltage across the SCR, right? So when we multiply the product of this current and voltage waveform, we may get the power like this. It may be, okay, 1 by 4 times the voltage across the SCR and current flowing through the SCR. Now, when I have connected this combination, that means a capacitor connected in series with resistance in parallel with the SCR, okay, what happens? Here we can observe one thing, that so the sudden change of rate of voltage is minimized, first of all, and secondly, capacitor is slowly getting charged. That means the voltage across, okay, SCR during charging period of SCR, during charging period of capacitor is slowly increased, okay, slowly increased. That means here I have shown linearly. Whenever there is no capacitor connected in parallel with the SCR, but when because of connecting a capacitor in parallel with the SCR, there will be slowly rate of change of voltage across SCR. During turn off period of SCR, okay, so due to the capacitor connected in parallel with SCR, current is reduced, okay, at the same time, but the rate of change of voltage across SCR is slowly increased. There is no sudden change of rate of or high rate of change of voltage across the SCR. So that means, here see, at any instant the magnitude of voltage is reduced compared to this voltage, okay, without connecting a snubber circuit. By introducing snubber circuit, there is a low rate of change of voltage across SCR. Then now if we multiply this rate of change of voltage with this current, so there will be reduced, okay, power dissipation. Because of the snubber circuit, here the rate of change of voltage across SCR is minimized, which minimizes the power dissipation, okay, across the SCR, right? So which is also known as the minimization of the power loss during the switching operation of an SCR. Now, what is the design of SCR? What is the design of SCR? Design of SCR means selecting the values of this capacitance and a resistance for a particular rating of SCR. There are certain ratings. Among them, there is specified dV by dt rating of this SCR and there is specified di by dt rating of SCR. So we need to choose the value of capacitance in such a way that it has to provide, okay, the rate of change of voltage in this circuit which is less than that of the specified dV by dt rating of the SCR, right? So then we have to choose the value of resistance in such a way that it has to provide the rate of change of current flowing through the SCR which is less than that of the specified di by dt rating of the SCR. So this is how we can design the values of capacitance and resistance for a snubber circuit. So that is why I can conclude like this: snubber circuit is a circuit in which the series combination of a capacitor and a resistor is connected across SCR to prevent dV by dt triggering of SCR and to limit high rate of change of current flowing through the SCR, and thirdly to minimize the power loss or power dissipation during switching operation of an SCR. So this is all about the design of snubber circuit of SCR. Thank you.